So this is still, we are still doing integration by parts. The table method is just a method that works with specific integration by parts problems. Okay? It's just a way to make your life a little easier on those. And boy, does it make it easier. So integration by parts, oh boy. Okay, so this is what I mean by using the table method. It's a different way to organize the information. And you use it when, if you were doing integration by parts, you'd have to do integration by parts multiple times. Like on the video last night, I think I did one where you had to do integration by parts twice. And I used red so you guys could see the difference when I was like doing the second part. Do you guys remember that one? That was probably the one where you were like, I don't get this. There are problems where if you were to do it by parts the way that I showed you in the video last night, you'd have to do it like 5 times. You'd have this like super long string of numbers. Would not be fun. You'd have to do it like 5 times. So this method is where we just use a table to kind of shortcut some of these steps. Makes you able so you can get the answer pretty quickly from that. All right. So you're going to use it. You have a polynomial. That's the trick. It only works if you start with a polynomial. You have to have a polynomial times, and it could be multiplied by e to the ax power. It could be multiplied by sine of ax, where a is just like some number. It could be a polynomial times cos to the ax. But the trick is that the first thing has to be a polynomial. So it has to be like an x squared, or it has to be like a 3x to the 5th. It has to be something with an x and an exponent. Or an x with no exponent, but it has to look like that. This would not work if you had like e to the x times sine. It would not work there. So it has to have a polynomial to start with. So here are here's the general form. So you're going to have 3 columns. The first column is going to be your signs. And I mean sign as in like positive, negative, like that. And when you do the sign, you're always going to alternate the signs, and you're always going to start with positive. Okay? So we're going to say alternate, and we're going to start with plus. The next column is going to have the u in it. The last column is going to have the dv in it. So the u column is where you put the polynomial. And you are going to take the derivative of the polynomial until the polynomial completely disappears. All right? So you're going to say derivative of u until it equals 0. So think about if we were taking the derivative of x squared, or our original function would say x squared. Our first derivative would say 2x. Our second derivative would be 2. Our third derivative would be 0. We're done. Does that make sense? So you just keep doing your derivatives until you're finished. With dv, you take the antiderivative, right? Because dv, we're going from dv to v. You're going to take the antiderivative to fill the chart. So the length of the chart is determined by that middle column. You fill out the middle column first, you do the derivatives until you hit 0, and that tells you how big your chart needs to be. And then you can alternate your signs, and then you can do your antiderivatives until you fill up the rest of them. Okay? All right. Over here, we're going to say, don't forget the chain rule. So the chain rule would have to do with your u. You might need to do a chain rule for part of that. Or u substitution. And the u substitution has to do with your dv column. So don't forget about u substitution, especially because that does show up in the dv column sometimes. All right, so the problem that we did last night at the end that was a pain in the butt was the, that's not a u, that should be an x. We integrated x squared sine x dx. So we're going to go ahead and redo that problem and show how much easier it could be if you use the table. So I'm going to start off with the u column. I'm going to say that u is x squared. What's my first derivative of that? 2x. What's my second derivative?
2.
What's my third derivative? 0. So that tells me that's how big my table's going to need to be. And then I can go ahead and fill in my signs. So I've got plus, minus, plus, minus. Okay. And dv for this problem was sine x. What is the antiderivative of sine? Negative cos. What is the antiderivative of negative cos? Negative sine. What is the antiderivative of negative sine? Cos. Okay. So we filled out the table. Here is how you find your answer. Your sine goes across with the u. So I'm going to use positive x squared. He's telling a story. He yelled. He calmed down.
That was Captain K?
Yeah. All right. So positive x squared. And then we go diagonally down like this. Okay? So positive x squared is being multiplied by negative cos x. So how should I write that down? So positive x squared times negative cos x. What does that give me? Negative x squared cos x. Okay? Then I do the next one. Negative 2x times negative sine x. Positive 2x sine x. Okay? And then I've got positive 2 times positive cos. Put a plus c on the end, and I'm done. So that was the problem we did at the end of the video last night. Way easier. So the table method, but it only works, again, it only works if you have that polynomial in the front. That's the only time it works, okay? And the reason that it works is because we're doing this middle column where we take the derivative repeatedly and it ends in 0, and polynomial functions are the only ones that do that. Sine and cosine, they don't do that, they just go on forever. Does that make sense? Yeah. So that's why when I was doing the video last night and I messed up, that's why it was wrong for me to be using sine and cos for my u, because that meant the problem was just going to continue, because that never ends. I could take the derivative of that forever and it's always going to be something else. Versus this one, you can take the derivative of it and it's eventually going to disappear and just be done. Okay, let's go ahead and do another one. You guys are nosy. You guys like read my email things when they pop up on the screen like that?
Yeah, of course.
Wow. All right. We're going to integrate x to the third, e to the 2x, dx. So this one right here, if you are curious, we did this process 3 times. That means that we had to integrate by parts twice. So it's 1 less than however many sets of arrows you used. Okay, so for this one, what is my u going to be? X to the third, so I've got x to the third. What's my first derivative? What's my second? What's my third? Or, sorry, that was, no, third, 6. And then what's my fourth? 0. Okay? And then we can do our signs. Plus, minus, plus, minus, plus. And then we've got our dv. So e to the 2x. How do I integrate e to the 2x? U substitution. Good. So we're going to integrate. Yeah, so my u is 2x. My du is 2 dx. That means I've got to take a 1/2 and put it in front. So I've got 1/2. And then I'm integrating e to the u, which is 1/2 e to the 2x. Okay, so this one's 1/2 e to the 2x. Okay? And then I have to integrate 1/2 e to the 2x. Yeah, you guys are like, I hate this. So here's what I'm going to write.
Just 1/4.
Yeah, I'm going to say the integral of e to the 2x becomes 1/2 e to the 2x. I'm going to keep that in mind, right? Okay. So now when I'm integrating 1/2 times e to the 2x, I'm just going to say that's a 1/2 in front of that integral, right? And I already did the math to figure that out. So I've got 1/2 times 1/2 e to the 2x. It's going to be worth it when you don't have to do integration by parts repeatedly. Right? This is totally worth it, yeah. So that gives me 1/4 e to the 2x. Now I have to integrate 1/4 e to the 2x. So that gives me 1/4 times the integral of e to the 2x, right? Which is just 1/4, and then I said my integral of e to the 2x was 1/2. And so it would give me 1/8. Yep, you're exactly right. So 1/8 e to the 2x. And then the last one would be 1/16. I can see the pattern. Okay. So how do we use this to get our final answer? Arrow over and diagonally down 1. So what's our first term? Okay. What's our next term? Okay. What's our next one? Yeah, she simplified that fraction as she thought about it. So 6/8 would be 3/4. What's our next one? And what goes on the end? Let's see. And how many times would this problem have had integration by parts?
1 to 4.
It would have been 3, right? So it's 1 less than the arrows. So it would have been 3 times. That would have been a pain in the butt. So we're glad that we can do it this way, right? Whew. All right. Example number 6. Another example. All right. We're going to integrate e to the x sine x dx. Is the table going to work with this problem? No. What is the primary reason the table does not work? There's no polynomial. This would never end, right? Because the derivative of e to the x is just e to the x repeatedly. And the derivative of sine goes to cos, then goes to negative sine, then goes to negative cos, then goes to sine, and it repeats. So the reason we can't use the table is because the table would not end no matter what you use for u. Does that make sense? Why we can't use it? Because we got to use ones that end. Okay, so think about late, L-A-T-E. Which letter goes with this problem?
Log.
So this isn't a log though, right? It's kind of an exponent. Well, it's a e to the x. What's another letter that we see?
T.
T. So I'm going to go ahead and use the sign as the u because this is trig. Okay? Right? T for trig. So I'm going to say u equals sine x. If you want to try it the other way, you're welcome to. I did not try that ahead of time, so I don't know if that's going to work out very easily. All right. Somebody tell me what the du is. Wait. Sign goes to
Negative.
positive cos.
What? Just kidding.
If you do the integral, you get the negative. So positive cos dx. Okay, so there's our u. What does that leave for dv then? E to the x dx. And so what's v? Just e to the x. Okay. All right. Let's do the arrow thing so we don't have to get our formula out. What do I write next? E to the x sine x. And then what do I write? Minus integral e to the x cos x. Are you guys seeing the problem that's about to happen here? Yeah, when we find the integral of this, what's our method going to be? We're going to integrate by parts again. And do you guys see how like the same thing's going to happen? Neither one of these are good to like be derivatives that eventually go nowhere. Both of these derivatives are going to keep going forever. Does that make sense? There's a trick to this problem that makes it kind of interesting. So we're going to do this one more time. I'm going to go ahead and switch colors because I am now integrating a piece of this and I don't want to get confused. So I'm going to take this right here. I'm switching colors. I'm going to integrate that part right there. So e to the x cos x and I'm going to set it up in a similar way that I did the original problem, and you're going to see why I do that in a second. We are being like super tricky here. We're being super tricky. So I'm going to say that the u is cos x. So what is the du? Negative sine x dx. And then what does that leave for dv? E to the x dx. And then what does that mean for v? E to the x. Okay. When I show you guys the tricky part, you're going to be like, all right. So this equals, there's a little tricky part where you're like, I never would have thought of that, because that's how I felt when I looked at it. I was like, that is the coolest thing. But I like math more than you, so you'll probably just be mad. Okay. So what should I write next? Okay. So e to the x cos x minus integral e to the x, and it's negative sine x. So is it okay if I take the negative from the negative sine x and like cancel it with this? Okay, so I'm going to cancel with that and then say sine x dx. Oh my gosh, that's the original problem. Okay, stick with me. I don't know if anyone's seeing ahead and they're seeing where we're going, but we're gonna go somewhere cool with this. Okay, I'm gonna write the entire original problem, but this red part right here I'm gonna replace with this red part right here. Okay? So I'm gonna start with the original problem. I'm gonna say that this is what I was trying to do. Some of you guys are maybe seeing it already. Equals e to the x sine x minus, and then instead of writing my red part from this box right here, I'm going to insert this red stuff right here. Okay? So instead of writing this stuff that was in that rectangle, I'm going to write this stuff because that's what it equals. So e to the x cos x plus integral e to the x sine x dx. Okay. It does not quite cancel. It almost cancels, but you're going to see in a second. So I want to get rid of my parentheses. I'm going to distribute my negative. Okay.
That's probably because I kind of
Alright.
Whoa. Whoa. All right. Now, think about this in terms of regular equations, right? When we solve equations in math, if you have an unknown, we usually use a variable for it. We use like an x. If you had an unknown over here, this is our unknown because this is what we're solving for. If you had an unknown on one side of the equation and the same unknown on the other side of the equation, what would you do?
We'd say x was x and all of it.
You would want them to be on the same side together, right? You don't want x's on both sides. You would want them eventually to be on the same side. So what I'm going to do, since this is the negative version of this, I'm going to add it over to the other side. All right? So I'm going to say plus. So how many of these integrals do we have? We've got 2 of them. And there should be, there's a plus C on here because I was integrating things. Okay. So at this point, if I go back to the original problem, and what my goal is I want to figure out what this equals right here. That's what I want to do. I need to divide it by 2. And then, did I figure out what that equaled? Yes, I did. I did it in a weird, roundabout way, but I did it. So what we want to recognize is maybe like what scenario this would happen in. So what about the original problem told us that we were going to have an issue with this? The e to the x just like continues forever. When you take the derivative of it, it doesn't stop, right? It just continues forever. E to the x, e to the x, e to the x, e to the x. Sine x does the same thing. It alternates between sine x and cos x. Okay? So looking at that at the beginning of the problem is what told us we're probably not going to be able to ever finish integration by parts by actually doing the process in a normal way. We're probably only going to be able to do integration by parts by ending up with something that we actually started with and moving it over to the other side like that. That was kind of the clue that we're going to have to do it this stupid way. Does that make sense? How I could maybe recognize that in the problem? Okay.